Hi, good afternoon everyone and welcome back for the afternoon session. I am Analisa Smoke and first I would like to thank God for bringing us together here once again with good health and happiness. And I also thank my teachers for giving me this opportunity to stand before you all. And without further ado, I now request session chair Dr. Sourav Roy and speaker Dr. P. Rangababu, NIT Meghalaya to come over the stage. Dr. Sourav Roy is the lecturer and head department of Electronics and Telecommunication Engineering, North Tripura District Polytechnic, Dharmanagar, India. Dr. Roy is the author of more than 30 reputed journals and conferences. He is serving as a reviewer for different international journals. His research interests includes metamaterials antenna, MIMO antenna, wearable antenna, and so on. So now I request Dr. Sourav Roy, sir, to chair this session.
Thank you. Hello. Thank you. Thank you once again for giving me this opportunity to introduce our speaker, Dr. P. Rangababu, sir, from NIT Meghalaya. Sir has serving as an assistant professor since August 2014 and head of Department of PC, NIT Meghalaya, in the Department of Electronics and Communication Engineering since 2009. Before joining NIT Meghalaya, he had worked as an assistant professor in NIT Goa from October 2014 to May 2014. He has 34 essay publications and 38 international conference publications, 8 funded projects. His research interests include multimedia architecture on FPGA, ASI design and embedded systems, and other accelerators for signal processing. So today I will discuss about the design of hardware accelerators on FPGA. So with this brief introduction, I welcome sir to continue the session.
Yeah, thank you, sir, for nice introduction. So I thank the organizers for having me a talk on design of hardware accelerators on FPGAs. I think from last 10 years I'm working on this domain, and today I'm going to discuss about what are the various methods are there for doing the hardware acceleration on FPGAs. Some of my student works I am presenting here, and also if there is a time is left, then I will show you a short demo on taking a FIR filter, how to accelerate the FIR filter. So first of all, my outline of the talk is need for hardware accelerators and about the FPGAs and case studies. So case studies of HDL based designs, case study of HLS, high level synthesis Python based design, case study of AI hardware acceleration based designs. So for all these designs, targeting different kinds of applications, varying different amount of computational overhead. So when we are going to the domain of computational platforms and strategies, when we are choosing any application, first of all we have to identify what is the right platform for this particular application. So that according to that we can develop the particular task. So if we don't have a large amount of if the applications needs very energy efficient, then we will go for software based applications where the instruction set is fixed. That is we call it as microprocessors and microcontrollers. And where we need a area efficient, energy efficient, power efficient, performance efficient, like the speed, so that we need FPGAs and ASICs. Of course, there are some other things are also there, such as GPUs and general purpose processors and all. But normally, the general purpose processor does not have a specific kind of instructions to accelerate a particular task. So, but GPUs is having certain kind of special resources, but they are power hungry. So we need to the application shouldn't take more amount of power. At the same time, it should reach the performance. That is the objective of the for any particular application if we wanted to accelerate on FPGAs. So again, normally FPGAs are designed for only the previously we are using for only module development. Maybe we are using for design of a processor and design of some low-level arithmetic modules. But now we can use the FPGAs for even SoC developments, system on chip development of one particular entire system. So where you need a hard-coded HDL is not sufficient, because if you wanted to develop AI, so it needs signal processing algorithm along with the evolutionary algorithms, along with the high amount of memory traffic. So all these things should be embedded in a single chip. So that needs a different strategies to deploy the systems. So for that you need to have a high-level system, high-level synthesis systems. So in design strategies we are using either RTL, high-level synthesis strategies on FPGAs. So why do you need hardware accelerators? Because one important aspect is the Moore's law. From Moore's law defines that as the technology is shrinking, more number of transistors we can accommodate on a same amount of area. But after some amount of time, when we are reaching to the 7 nanometer, even the transistor size is shrinking. You cannot accommodate more number of transistors. So you need a different strategy. So then we come across, instead of decreasing the size of the transistor, how to efficiently port the algorithms, how to map these software algorithms by using separate strategies like parallel processing approaches to implement on FPGAs. So what are the demands for these hardware accelerators from the applications? So we need computing demands. So where one particular application task, you need to implement like the particular task requires more amount of computational demand. For that kind of task, you can accelerate through the FPGAs, and you need to store large amount of footprints at a higher speed. For that kind of applications also you need the FPGAs, and multiple application requirements. Let's say when we are developing any system, if it is an ASIC, forever it becomes one particular application. But if we wanted to reconfigure like a software flexibility, how a software flexibility is there? Like if we change the software executable code, then automatically the application will be ported to the particular platform is ported to the different environment. That kind of flexibility is required when we need for multiple application requirements. And cost of equipment, which shouldn't be more costlier as ASICs. And time to market is very important when we are developing a system. because shorter time to market will produce the more productivity, so that your cost will be less, and low delay and high performance. So these are also some of the requirements, and energy efficiency depends upon the application. We are targeting any one of out of three, any one of it we will target it. So this is the implementation alternatives: general purpose processors, application specific integrated processors, microcontrollers, and DSP systems. And the power efficiency is high for ASICs, but flexibility is more for general purpose processors. But in FPGAs, either the flexibility and power efficiency both are good. That's why they are using that as prototype devices. And why we are not using CPU? CPU is having a specific instruction set, and which contains the powerful ALU, large caches, and sophisticated control, but which needs more amount of power also. And the size of the system is also large. And where the instruction set is fixed, we cannot change any execution of the instructions. So even though the CPU provides the pipelining the execution, it increases the performance of the execution of the instructions. But finally, the processors working on a sequential execution, even with the multiple processors, you can at the same time, but the power also will be increased. So GPUs require small cache, simple control, energy efficient ALUs, but normally used for computer graphics applications, and other hand they are power heavy. And comes to the field programmable gate arrays. Field programmable gate arrays is similar to like programmable logic arrays, but here the CLBs are made up of lookup tables. So any kind of Boolean logic function can be mapped onto these lookup tables. So, and important thing is that along with the lookup tables, you have a DSP blocks. So where we can map a high performance function onto the DSP blocks, and we can use a on-chip memory where you can store large amount of information at a higher speed. You can deliver to the logic. So these are the features of your field programmable gate array: configurable logic elements, memories, DSPs, different clock regions, and input and output modules, and built-in IP cores. Along with that, you have a flexibility that you can develop your own IP, intellectual property of your logic. Like if you are thinking that okay, I wanted to develop my own FIR filter on the hardware, that you can develop. If I wanted to develop my own, I will show you some of the slides where we develop our own SSA intellectual singular spectrum analysis hardware code to accelerate the singular spectrum analysis code. So, what are the differences between FPGAs and ASICs? ASICs are more powerful and provides the more performance, but FPGAs are prototyping devices. But they are prefabricated programmable components and faster turnaround time. Before taking any commercialized ASIC chip, first of all you have to prototype on the FPGA so that that particular application will be deployed in your lab environment itself. So that is one of the advantages that you will get. Where ASIC needs, if the chip is fabricated, then only you can identify that whether the chip is after testing of the chip, then only you can identify whether the chip is working on. But here, FPGA you can use in lab environment and you can test the device. So compared to the CPUs and GPUs, higher level amount of parallelism, because in GPUs you have fixed amount of data types, but in CPUs also you have a data type is fixed. But in FPGAs you can go according to the requirement of your bit processing. And if you need a real-time performance, you have always you can improve the throughput by strategies like pipelining and parallel processing, you can use it. And you will get the higher efficiency, and even you can use the security features also. Okay, so this is what previously the microcontroller is contains the system on board, where we are 8085. If you look at all the peripherals are outside. Now all of them are connected into a single chip. So where this is your FPGA. Previously we are using only to using these logic resources to make a one full adders, half adders, and arithmetic modules. But now, since there is a processing system that is inside of the FPGA, you can connect these processing system to the programmable logic, and you can develop the systems. So a processor along with the peripherals and the bus, you can make a single SoC system. The peripheral C, you can develop your own customized hardware accelerator. Maybe a 4096-bit adder, because the 4096-bit adder is not available in your instruction set. So if you wanted to do 4096-bit adder, that is what the cryptographic applications and all. Normally they usually have 128-bit, 256-bit and all. So if you wanted to perform that kind of operation, so general purpose processor does not have that many bit processors. So you need more number of clock cycles. But here you can develop your hardware using the efficiently on the FPGAs. So where not only that, the FPGAs you can use for developing the real-time systems, where operating system also you can keep, and then you can use as good as your embedded microcontroller. This is what the one Jink device, which is provided by the Xilinx. So we are in lab environment, we are using these kind of devices in our labs. And here the important thing about the buses also plays very important role when we are developing the systems, because it depends upon whenever you wanted to fetch the data from the memory to the processor, it takes more number of clock cycles. So the data transfer time is the bottleneck for any system. So if you reduce the number of transfer times, so your performance will be more. So with that goal, let's say if I wanted to have a 128-bit adder, or a 256-bit adder, or a 4096-bit adder, once only I will send the data, I will keep the one FIFO and I will store all the data. Once the FIFO is full, then I will send the data to the adder, then it will do the operation and again return back to the processor. So you don't need to consume more number of clock cycles. So for that you have a different kinds of buses. Memory mapped buses contains AXI full, AXI light, and stream. Stream is a point-to-point communication kind of a bus which is used to develop like co-processors. So memory mapped is a kind of a bus which can be used for bus arbitration will be there, so that you are connecting the bus to your intellectual IP, and other side you have to connect to your processor like this. So the peripheral is connected to the IP, and the peripheral is connected to the bus is connected to the processor. So processors is also having different kinds of ports. Depends upon how much bandwidth that you wanted to get a transfer. So you have a high performance ports, you have a general purpose ports. So depends upon the data transfer rate, you are connecting these peripherals. So according to that, the peripherals are also connected. So this is the system development. So what is the first step when we are developing the system? So any application if you take, so first of all we have to do the profiling of the system. Then only we can requirements. Then it starts with the specification. Then you have to partition the design. The hardware software co-design involves partition the design. So for that you need to do the profiling. I think most of the people we are using Intel or any other processors. We are doing the profiling using some Intel profile analyzer or GPROF, genuine profiler, like that if we use, so that we can identify the where the computational overhead is taking in a particular task. So those things, if we map it into the hardware, so that that particular task will be is taking the less number of clock cycles, so that you can improve the performance. So where the system design hardware software partitioning is very important, and after that you have to develop the hardware. You have FPGA, so you have to write the HDL code, and you have to implement the design. I will show you the hardware part and also software part. I will show you in the coming slides. So what is that here? So you have a software environment, you have a hardware environment. Software is how you are using the general microcontroller. You deploy the software application as it is. But here the difference is, in the FPGA you have a one processor, you are targeting that particular processor and you are implementing the application. And during profiling you are getting some kind of point that where the hardware acceleration is need to be achieved. That thing you do it in the hardware and design the particular hardware using two different approaches. One is RTL methods, another one is HLS methods. Using that, you can integrate onto this SOC platform, and you call that particular hardware function of the software. Then you can see the performance. So since this is not using the instruction set architecture of your processor, it is directly using the logic resources of FPGA, which gives you a more performance compared to your instruction based execution. So that is what here. So this is the one example. You can do the DMA, you can connect the DMA. So we will show you one demo we are having a ARM processor where a FIR filter is connected. Using the FIR filter, we are sending the data from the processor through DMA to the FIR, and again the result, once the result is got, then that result again back to the ARM processor. Again, both the performance we are compared, software versus hardware, so you can see the real-time performance. So here the important thing is that here in this slide is, so you can develop a system in a multiple number of ways. So if you are writing a gate level code, it takes millions of gates, but it takes large amount of time. So if you are going for an industry, definitely one look for shorter design time. So whenever you are targeting gate level or RTL level, which gives the performance 4x times compared to the high level behavioral times, but that has required more design time, more number of people are required. So that is why now in research in all the domains, what we are doing is, what the even industry people are doing is, first they are prototyping for functionality verification, they are implementing everything in the behavioral. So they are getting some acceleration, they are getting some kind of performance compared to the software. So later they are optimizing using the RTL level or gate level. Okay. So that is the strategy, so that we can improve the performance at the same time we are having a product in our hand. So first of all, now I am going to the case studies of my students. So I think 2 PhD students are done in a similar domain, where HDL method implementation on FPGA targeting towards the ASIC. So where you need high performance, energy efficient. After one big system, you are working for one small module, where if the module you are accelerated, then the overall performance of the system will be increased. Okay, so for that you need knowledge of HDL, thorough understanding of the algorithm in all the points, so that once you understand the algorithm, then only you will know where I can analyze the algorithm. Then computer architecture concepts. So how to efficiently use the memory processing. Okay, so for that also we need, and also EDA tools and FPGAs. So what we are doing is, in the first case study, we are having a one full, let's say, a carry to header. So carry to header is having some specification. We have to perform a 64-bit carry to header. This carry to header is the part of a bigger processor. So for that, first of all, if I'm targeting the processor, then entire thing will be takes more amount of time. So that what happens, I will target only the carry to header, then go to the design entry, and then we are doing the functionality simulation. Either gate level, there are 3 or 4 approaches are there. So behavioral level, structural level, gate level, you can do the simulation of at various levels, and then you can perform using synthesis with the EDA tool. So I think the example of the one full adder RTL shown here. So once you are doing the simulation, you are getting the simulation functionality like this, and after that you are converting that into the synthesis, means you are converting into the gates. Then you are implementing this particular design onto the FPGA by according to your timing requirements, according to your how much amount of area is sufficient. Later, you are implementing that, and that FPGA chip will be behaving as that particular design. So here, placement and routing and timing analysis and board level verification. Okay. So here, what my student did is, two students did is, first one person is working on deblocking filter of a HEVC, high efficiency video coding codec. Okay, so a video coding tool, where whenever we are sending any video or whenever we are capturing any video, we are not working on a raw video, because raw video takes, even if you are taking a 1 minute of video, 1 minute of video contains a resolution of 1920 into 1080 into 24 bits of RGB into 24 frames per second. Means for 1 minute you imagine how much amount of data that you need. So for that kind of thing you need to have a compression. So in the compression, HEVC is one of the codec that is used for multimedia video compression, where deblocking filter is one of the module. So there is a lot of pixels are there. We are trying to filter out when there is a edges. During the edges, we are trying to filter out the edges. There are different kinds of. There is a intra-prediction. So when it falls into the edge. So whether it is an intra-edge, then you have to do with one kind of filtering. If it is an inter-edge, you have to do with one kind of filtering. So these are the, according to the boundary strength, we are doing some filtering operations. So this is the one computer architecture, like how your processor is there. Similarly, we are carefully designing all the modules with each and every module. Let's say here there is an input buffer, there is a multiplexer, there is an edge filter, and there is a parallel edge filter. So if you see, there is a 4x4 parallel edge filter, and again all these modules are working in a pipeline manner. So stage 1 in conjunction, stage 1, if you see here, when stage 2 is working, stage 1 is also working in the second during the second clock cycle. And when stage 3 is working, stage 2 and stage 1 of the third block also is working. So like that, we are developing one kind of architecture which is published in IEEE, and this is also one more architecture which is, see, whenever we are sending any pixels without dependency, here the beauty of this architecture is, here we are not working on the this data path side, but instead processing side processing side we work, and in the memory, in the internal processing of the memory only, where without having any dependency of the pixels, we are processing. So that what happens, the developing filter is done in an efficient manner. So these are the simulations. So where you have one module, you are writing on the RTL, then you are implementing on FPGA, and you are generating the synthesis, and you are and carrying out the timing and routing and placement, and after that you can verify your design. And finally, whatever the module, since we are targeting this is from asset, so what happens? I think the student is performed 3 types of architectures. So one is providing area efficiency, one is providing speed efficiency, one is providing medium between both these two. So the user can have, depends upon my video data, I can choose any one of the filters. So that is the one thing. And here, motion estimation, one more student performed the submitted his PhD thesis on this motion estimation. So he performed the TZ as such. So when you are taking 2 frames, there will be a lot of redundancy will be there. So how to reduce the redundancy using some kind of search algorithms. So this is a one kind of search algorithm which we call it as a fast search, test zone search algorithm. So where at first we are doing rectangular way. Then after that we are going to the outer blocks. So that according to that we are doing the motion is there on the nearest neighborhood pixels or not. So like that we are doing the searching, and this is the hardware architecture for that motion estimation. And here also we are identifying that this particular architecture is providing higher performance compared to the other strategies if we use parallel processing approach. So these are some of the things. And the second case study is a very important and a very useful case study, which we call it as a HLS design based method. So where previously we are using HDL RPL level, we are not using RPL because it takes for one PhD student he spends 5 years of time. Then only he can able to complete with the 3 works. So we wanted to make one complete prototype kind of. So for that we thought to use the HLS methods. Then for that HLS tools, C and Python is required, RF SOC FPGA is required, that is we call it as Pink FPGA, and AXI protocols, knowledge on AXI protocol, and debugging, all the skills are required. So here, this is one project which is funded by BRNS. So where we are using the nuclear quadrupole resonance. So in nuclear quadrupole, it's like a one-dimensional NMR. Okay. So I think in physics and everyone they are using a two-dimensional 2D NMR. So this is the same time, but it is a one-dimensional. If we are performing at one-dimensional, that is called NQR. So in NQR, it is a solid-state radio frequency kind of a technique. So where in narcotics, in food analysis, this is usually used. And the signal is like contains 2 kinds of parameters. One is exponential and other one is sine. So the objective of this particular design is to identify a particular substance. Let's say if it is one tablet is there, how much amount of that particular material is there. We have to identify. For that, because since it is RF, there will be a lot of RF clutter will be there, and also and the noise will be affecting more to the signal. So we have to come up with one denoising method, so that the pre-processing should be done before identifying the material. So what we are doing is we are writing a C++ code and check the synthesizability. Then C-level verification is done. Then we are trying to parallelize the application where we can get the more amount of performance. Here the language itself is having some kind of constructs are there, using array, using loop, using function. You can parallelize the one particular C. You can particularly on C function you can parallelize it. Okay. So after that you can generate the RTL code. So that RTL code we are using again to implement on the gate level and place and route and chip and implementing on PCA chip. So where you can get in the previous slides I shown 7x acceleration you used to get. So this is what. So we are generating the HLS and then we are integrating onto the one SOC system that we develop that is integrated as an intellectual property of this system. Okay, so this is the functional verification at each and every level. More or less it is same. So finally you are implementing that on the board. So this is the algorithm that we are talking about. This is a singular spectrum analysis. The challenge of this particular system is it is a matrix contains, like let's say one signal contains 4096 samples. So you have to convert a one-dimensional. We have to make a covariance matrix. If we wanted to make a covariance matrix, then it becomes a matrix of two dimension. So you have to process a large matrix of 4096 into 4096. And that too, after that you have to perform all of your operations, calculation of eigenvectors and identifying the principal components. After identifying the principal components, and then you have to do the diagonal averaging. So this is a tedious task. If you are performing an 8 cross 8 or a 256 cross 256, then it is easier. But if it is performing at a 4096 cross 4096, even in normal CPU itself, in your MATLAB itself, it is takes lot of amount of time. So how to increase, how to accelerate this particular application? The specifications of the signal is 3.8 megahertz, sampling frequency is 32 megahertz, decaying parameter is 0.5 millisecond. For that particular signal, this whatever the signal that I showed to you here. So here, so sampling frequency, specifications, all these things I provided here. So we tested initially in the software environment. So this is the signal, this is the denoised signal. So we have to identify that denoised signal after performing the SSC. So after performing how to identify that whether I denoised the signal or not. So I will apply the fast Fourier transform. It will identify that what is my signal frequency is there. So with different noises adding into the system, then we verified the signal to noise ratio, and even in the cursor level we identified that the signal is buried, and the signal is buried. Again, it is denoised onto the SSA algorithm. So these are the different approaches. Now this algorithm we wanted to map it on the pink FPGA using HLS. So there is no eigenvalue, like eigenvalue computation itself is a very tedious task, because for finding a bigger matrix and performing the eigenvalue computation is a tedious task. And here the important thing is that I think the student is come up with a power method. Using the power method, he can identify what are the main principal components are there. So we need first time eigenvectors only. We don't need all the eigenvectors of the complete 256 cross 256 or 4096 cross 4096, because the signal features are there in the in the first principal components group. So using that we can reconstruct the signal. So for that you come up with a power method. So using the power method, that also we kept in the pink. So this is the complete system. So where you have a pink zinc processing system which contains the high performance code and connected with the DMA and the intellectual property core, which is your SSC algorithm. That is connected with the IP core, and since DMA is required, why? Because so you need to process 4096 samples at a time. So using DMA, you can maximum you can send 256 samples. 256 samples through burst. You can send 256 samples. So like that, we are sending all the samples and does the operation on the IP core, and then we denoise the signal. So this is these are the results that are obtained on the FPGAs. So finally, these are the resources. Here again, you can. One good thing is that if you are working on software approach, only you have only one kind of method. But since it is a FPGA, you can make parallelism and you can increase the number of levels of parallelism depends upon the resources. So you can efficiently use the resources so that you can get the more amount of performance. So this is what we tried for. What happens if my design working on floating point and fixed point? So what about the resources? So if I am using the fixed point, then LUT resources are reduced. If I directly mapping onto the floating point, more number of resources, it consumes 100% of resources. If resources are more, power consumption will be. So we try to reduce by optimizing the design using the fixed point. So finally you got RMS error with respect to the software versus hardware. So almost 1.10 into 10 to the power of 5. So it does not have very much the small amount of difference between the software and hardware, and it provides you a better performance. So how much is the performance? And later I will show you what is the acceleration that we got. Along with that, the student is attempted one more important challenge. So now you got the signal, but from the signal you have to identify the signal characteristics like phase, frequency, and other parameters. For that, Levenberg-Mark-Pitt algorithm. Levenberg-Mark-Pitt algorithm is one kind of optimization algorithm, which is used to non-linear least square fit algorithm. So we used Levenberg-Mark-Pitt algorithm. So we are using exponential curve fitting and using frequency. First of all, we have to identify the envelope of the signal, and second part is the frequency and phase we have to determine, and then we have to apply the non-linear least square fit, and using Levenberg-Mark-Pitt algorithm we can identify those parameters. And using here we are applying the denoiser algorithm. Since the signal of interest is denoiser algorithm, we have to apply as an input, and then we are performing the non-linear least square fit on the hardware. So again, here also we get a very good performance. Since these both the designs needs more number of resources. So this after finding the Levenberg-Mark-Pitt algorithm, these are the input and output. And what are the error that is between the software and the hardware also we reported. And what is the outcome of this work is, so we are getting a non-linear least square fit, we are getting a 35.6x acceleration compared to the software. And when we are comparing the SSC algorithm on hardware, which is providing 15.48x acceleration time. So this is I think first of its kind of work. So similar kind of FIR filter design we prepared. At the end of the session, I will show you step-by-step approach. Since it's a tutorial session, I wanted to give one tutorial to the students so that maybe some of them will get benefited with their research work. So the next thing is, this is also which I just started in this domain from last 2 years. So where FPGAs are for machine learning. So where we need Python, C, HLS protocols, and along with the TensorFlow, GPU tools, FPGA, EDA, so many domains is involved in this area. And thing is that you are developing an application on the you are developing an application using some kind of framework which is TensorFlow or any other framework. Then finally you are deploying on the any of the devices like edge devices, GPU or TPU or FPGA. So when the AI tools are becomes mature, so you need a large amount of, because day by day the more approaches are required, more number of layers are required. For that you need a larger amount of footprint, you need a larger amount of computation. So for that you come up with a FPGAs with a more performance oriented. So efficient AI algorithms building on hardware accelerators in tandem, we will develop this kind of applications. Where in these applications you may use signal processing algorithm acceleration also. So it is up to you that how efficiently you are using your FPGA. So this is what. So develop the model in Cafe, write the HLS code on a particular model, and then using HLS tools you deploy. Okay, but we come up with a AI flow which is available on Xilinx. So where we are taking the image segmentation. Okay, image semantic segmentation. So this is the city-scale data set. We are using the BGG19 model. We are using unit model. So here two things are there. From this, here we wanted to reduce the quantized weights of a particular model so that the power of the entire system will be reduced. So instead of using floating point, we are using fixed point, so that this becomes not a power hungry application. So for that, you need to use the YTC AI platform. Of course, different tools is having different ways. Since we are using the one method, we are following this way. So in GPU, first of all, you have to train the model and you have to find out the weights. After that training is completed, then the weights you have to update to the YTCI platform and come up with a DPU design. So how you will do the DPU design, I will show you. DPU design is generic. Once if you design for one system, it remains same. You implement on that DPU system what model you want. Only thing is that whether that will be fitting to your DPU or not, you can verify. So if any HLS other algorithms are needed, you can keep into the DPU design and then you implement on the board. So this is the YTCI stack. So in our lab we have a ZCU104 and Alto 96 boards. So the students use the YTCI stack to develop this method. So first of all, in the procedural, what he did is, so choose a problem to prepare the data set which suits to your problem. Choose the network. So we have to come up with a network on the GPU, then train the network on the GPU, and whether you reach mean IOU or F1 score, then quantize the network using whatever the available quantitation parameters are there. Then evaluate the again mean IOU. So whether your performance is similar to the software performance or not, means GPU performance or not. Once you are satisfied with your network, then compile the model and freeze the model. Then you can take to the software development kit and create a Linux application and then create a bit file. That bit file you can use it to the system and then you can deploy. You can deploy on the FPGA and you can verify the system. So like this unit model, we performed this unit model used Cityscape dataset, and then we trained on the GPU and then deployed on the FPGA. Okay, so these are the procedural steps. Just what I told in the flowchart, the same thing here. Then quantization we applied, and this is the model that I am talking about, which contains the PLPS. So where the gene processing system, along with where the processor is here, and again along with the DPU is there. On the DPU, your model is deployed, and the DPU contains how much, some amount of RAM usage, number of layers, and the ReLU type, and you can say what kind of ReLU that you are, what kind of type you are using, and all these things you can configure it, and then you can see the how much amount of resources that is consumed, and these are the plots that we got from the GPU as well as the FPGAs, and these are the results obtained. I think the image that we got from the FPGA is black and white. So when we are seeing the image, it is capturing all the objects that is there. So when we are doing floating point, one of the important things is that you have an integer 8, you have a 6-bit quantized and weight are 8-bit quantized, integer 4. So these are some of the things are there. If you see, mean IOU is better in integer 8 when we are using. So the average forward pass of this Xeon CPU Quadra RTX 500 when we are using unit, so 145 milliseconds and power consumed is 178 watt. Whereas your FPGA is used more amount of time, but it gives you a very less amount of performance. So with the same application, with the same amount of accuracy. So that is one of the important about this particular application. So finally, I wanted to conclude here. So FPGAs are lab prototyping devices before making the commercial ASIC chips. From the case study 1, we can observe the first point. From the second, we can develop a complex SoC systems where some of the parts, some of the software algorithms, if you wanted to accelerate and develop the system, then they are also used. But you need a RF SoCs or RF SoC SoC devices of FPGA and other India tools. And FPGAs in conjunction with the HLS tools will provide a faster productivity and faster proof of concept implementation result that will be very useful for our research. So because whether these results, whatever we got, whether that will be useful or not, we can initially only we can identify that whether if I'm putting this block onto the hardware, whether it gives you a performance or not. So otherwise, after some amount of time, if we spend and if we are not getting the performance, then the total time will be wasted. So that is why very important. And FPGAs are used one of the alternatives to deployment as compared to the GPUs. So I thanks to everyone. Thank you one and all for providing me an opportunity. If any questions are there, you may ask. So maybe I taken more amount of time.
No, you are in time. Before time only.
If you are having 10 minutes, I will show you the demo.
10 minutes.
Just where is that slide? Whether this one is
3:45.
Can you open that? Is connected. Slower. So thank to all the MTech and PhD students of my group, and also some of the slides are taken from online, and yeah, this is the basic FIR filter. So I think whenever we are developing any system, this is the one of the digital filter when we are implementing. This is very useful. So when we are having a one signal which is corrupted with some noise, and if we wanted to do it on the real time on the hardware, then it needs a lot of effort. So here this environment, this FPGA environment allows you to do the easily. Okay. So where we have two kinds of filters, and finite FIR filter, we have finite impulse response filter we use, and these are the some of the requirements of the FIR versus IIR. So basically, I'm not going to tell about all the theory because already we are gone through all the theory basics. Just I am interested towards the design of the FIR filter. So FIR filter is having a one kind of a function which is k equal to 0, m minus 1, dk, z power minus k. That we have to effectively use. So see one convolution operation we have to implement along with the input and along with the input and filter conditions. So for that we are implementing software implementation directly on the Python. So where we are using SCPI and NumPy library, and some of the advantages like how So we are using fast Fourier transform and to determine the whether after performing the filter, after performing the filtering, if I am using the fast Fourier transform, whether I am getting the at the same frequency the signal or not. So this is the some kind of online resource is there where we can generate the filter coefficients. It looks like a same MATLAB FDA tool. Okay, so our importance is that to getting the filter coefficients in the quantized way. And then we are going to the Jupyter notebook. So when we are going to the Jupyter notebook, this Jupyter notebook is opening on FPGA platform itself. That means before going to the Jupyter notebook, so we have to take a FPGA, ping FPGA, and then we have to take the image of ping, and we have to deploy onto that FPGA. Then you will get this Jupyter notebook. So how to deploy that particular image and all, it is there in the good resources are there from the ping website. You can go through it. After that, you are getting this Jupyter notebook environment. So where you can write your FIR filter in Python. So this is a simple FIR filter. We can write the FIR filter how we are writing in the MATLAB environment. So you are generated the basic signal which is at 200 Hz with a 200 Hz and along with the sampling frequency. Then what happens when you are doing the fast Fourier transform? So if you are applying the 200 Hz, so you will get the 200 Hz signal at the Fourier transform. So then you are connected the signal with a noise. So then now the thing is that we wanted to denoise the signal. We not denoise the signal, or we wanted to use FIR filter. So to FIR filter to generate the exactly 200 Hz signal. So I am using the FIR filter. Then the mixed signal and the filter output we are mapping onto at same time. Okay. So afterwards, then till now the story about here is only the implementation of the software. Everything is there in the software environment. So now real usage of FPGA I wanted to utilize. So then we have to use the Vivado HLS, or maybe directly there is an intellectual property of FIR filter is there. Directly you can take. So here already there is a inbuilt FIR filter function is there. So that we are taking. So from that directly we are connected to the FIR filter, and then whether the hardware FIR filter is having better performance or not. So then we implemented this design. So I think we shown the step-by-step approach. So where this is the Vivado design. From this Vivado design, you can add the processing system, means your processor, and then you are adding the FIR compiler. FIR compiler will provide you will perform the FIR function. Only thing is that you have to apply the coefficients here that you got from the open source link. So you are putting the FIR filter coefficients here, and then you are connected to the processor. So all these systems are working with the master and slave communication. So if the processor is master, then your FIR compiler will be the slave. After that FIR compiler output, again you are giving back to the slave of your processor. But instead of directly giving to the processor, what you are doing is, since you have to process the samples to the FIR, you have to send the signal to the FIR compiler. Then only the convolution operation is performed. For that you need a DMA. So here the AXI DMA that we connected. So the AXI DMA along with FIR compiler, both together that we are connected, and then these two modules we are connected to your processor. That is what here it is shown in the down. Okay. After After we are connecting the filter along with the DMA to the processor, then you are generating the bit file. After the bit file, you are generating this everything into the TCL file. Then these two you are copied onto the pin code environment that I showed previously. You are creating an overlay for that particular design, so that you can use this hardware accelerated FIR filter on the software environment. Okay, so these are the software, what is overlay and all you can use for multiple applications. Not only for this one, not only for logic one, and again you can use for I2C, UART, other peripherals also. So the intellectual property here is your FIR filter. So here, using the different functions like XLMK and DMA, and these with this you can write your ping on the software environment of the ping. You are calling this overlay. So I think the first overlay is equals to overlay into bit file. Means you are calling your bit file. You are calling your bit file of implemented hardware, and then from that you are calling your DMA FIR filter. Then if you are writing all the lines of code for calling those DMA, sending the data and receiving the data. All these lines of code you written, and then if you are verifying the software versus hardware execution time, so your hardware FIR execution time is taking 4 milliseconds. So the hardware acceleration factor compared to your software execution time is 20x. So this is a very, like in a lab environment, just we are implementing a small application like FIR filter. So you are getting a 20x acceleration, and again which is similar to your and after when you are performing the fast Fourier transform, again you are getting the similar response. So this is we wanted to show to everyone. I thought we wanted to bring the PCA kit and all, but because of very limited amount of time we are unable to do it. But I hope this one will be very useful. So using the same strategy, you can deploy any kind of hardware accelerated applications. Yeah, thank you one and all. So any questions?
One question is
actually, not a question that just a small thing. You have been given on the CDSK data set.
Yes, sir.
And the last thing you have showed the outputs are black.
Yeah, actually, if you open in the laptop, you are able to see, because we are captured using the what is the grayscale image, because we don't have that much amount of memory to store the image after when we are
the pixels is black. Okay.
But even afterwards, we done the similar kind of application on even classification problems. Classification problems are also working fine. So we are about to publish that one also.
Sir, one question is that clock speeds are typically an order of magnitude slower than processor due to delay overheads through the general routing matrix. How could we exploit the full potential for
Okay.
that question come from our
Okay.
live.
Understood. So here the one very important question, because when we are making any design, so normally when we are making any application, we are running at 2.7 GHz, or even your ARM processor that is working on FPGA is working at 1 GHz. But your hardware is working at 100 MHz. But 100 MHz one is giving more performance because 100 megahertz is getting more performance. How to exploit the full potential of the processors. So here, important thing is that you have to develop your hardware accelerators. You have to make your hardware accelerators more design these hardware accelerators which can accommodate larger frequencies. Normally, we used to work with these bus frequency, which is bus frequency we are kept at 100 megahertz. That is one of the bottleneck of these SOC systems. But in gene processors and all, we can increase that where we can have a point-to-point communication, where we can increase the performance of the bus as well as this IP. I hope I answered your question.
Okay, is there any other questions? Anyone have any other questions?
Sir, what kind of filtering technique usually involvement of filtering techniques in the brand?
Here, I think we taken generalize the window only. I think we didn't done. I think general window. What kind of window technique we use?
That general, because we are mostly focusing on getting person as creative.
Yeah, actually, this is just like you think about is a form of a convolution. We are not exploiting any window technique because we can use Hermite window or any other bezel window or some techniques that we can use. But just I want to tell you we are not focusing towards the high performance of FIR filter. We are focusing towards how to rapid prototype of FIR filter on the FPGA. So it is just we think that is a kind of a combination.
Thank you, sir. Another question from our YouTube session. An FPGA potential for massive parallelism frequently complicates arbitration and speed.
Yeah, actually for this also there are some kind of like one of the things that I used is debugging. So in the debugger we have a hardware co-simulation as well as the debugger environment is there. Using that we can check. But even there is a BFM, bus functional model simulation is there. Using that also we can, that is simulator only. But if you are using a debugger, in a real time manner, you can verify you can monitor these contention. Any contentions are applied between these different IPs. Are there or not? We can verify. Yeah.
Sir, one question just. Okay. Sir, sorry, I was listening to you, but in between I didn't hear. But I had a question to you over there. Actually, this FPGA, it can be used as a tool for designing the ASIC.
Yeah. It is a prototyping device before making ASIC.
That is not good. So my question is that, is there any possibility that whatever you have implemented in FPGA and final implementation in ASIC, is there any possibility of any differential parameters or any kind of...
Definitely, the performance is much better than compared to your FPGA because your delay. Here, large amount of routine delays are there in FPGAs. Whereas in ASIC, you have a standard cell. So in the standard cell, you are having your resources are fine-tuned. So that you will get a better performance. If you are getting 100, if your design works at 100 megahertz, definitely your design may be working at 150 or 200 range. Or even resources also it will be massively reduced so that power consumption also will be very less. But that is why FPGAs we have to see it as a prototyping and functional verification before making an ASIC. Because ASIC contains again large amount of money is involved.
Yes.
So before making an ASIC chip, we have to succeed in the FPGA so that it will be very useful.
Okay, I hope there is no any other questions. So thank you, sir, for your interacting session.
Thank
You
you.
covered all the questions raises from YouTube channels as well as our participant side. So I hope in near future also you will participate or you will join in our different programs as a session chair or any other position. And thank you once again from our committee as well as from me. Thank you, sir.
And all the organizers and also session chair of this particular conference, and especially Binam sir. So thanks, and also the organizers from the COMSIS. Thanks for your.
Sir.
I request our chairman, Sir Dr. Sourav Roy, to facilitate our speaker, Sir Dr. P. Rangababu.
Thank you, sir.
Thank you, sir. And now I request Dr. J.D. Swanagar, sir, to facilitate the session. Chair Dr. Sourav Roy.
Yeah, this is good.
Sir. And now we will begin the inauguration ceremony.
Thank you, sir. Sir,